Now let's study the next application of sine rule and cosine rule, that is area of a triangle. Now area of any triangle ABC is given by half AB into sine C, which is same as half BC into sine A, which is same as half CA into sine B. So let us try to prove any one of the part so that the remaining two parts can be proven similarly. So here we now see the proof of area of triangle ABC given by half AB sine C. So to prove this, we use a similar approach that we used in proving the sine rule. That is, we consider three different cases in which the triangle ABC can be either acute angle triangle, obtuse angle triangle, or a right angle triangle. So accordingly, here we have the three cases. Now we are considering BC as the horizontal side, which is shown at the bottom in all the three cases. From the vertex A, we drop a perpendicular on side BC, and wherever it meets that side, we call that point as D, which is the foot of perpendicular. Now in third case, since angle C is a right angle triangle, D will coincide with point C only. Now in the first case, that is when angle C is an acute angle triangle, angle C is acute angle, in that case we can write sine C as the opposite side upon hypotenuse, that is nothing but AD upon AC, which is nothing but AD upon B, because side AC is nothing but denoted by B. So therefore on cross multiplying we get AD is equal to B sine C. Now in the second case, we observe that this is angle C, but the adjacent supplementary angle is pi minus C. So therefore sine of pi minus C is nothing but the opposite side AD upon the hypotenuse, which is nothing but AC. And we know that sine of pi minus C is same as sine C. So sine C equals AD upon AC is nothing but B. So once again here also on cross multiplying we get AD is equal to B sine C. And in last case, C is a right angle triangle, so we can write sine C as nothing but 1, and that can be further written as AD upon AC, simply because AD and AC both are of the same length. So therefore we can write sine C to be equal to AD upon AC is replaced with B. So therefore finally on cross multiplying we get AD is equal to B into sine C. So by this we have shown that no matter what type of triangle it is, AD is always equal to B into sine C. Right? And here we observe that AD can be considered as the height of the triangle if we consider BC as the base. Alright. So at the end we write the expression for area of triangle, which we have used since long, that is half the base, that is BC, into height, that is AD. Right? So therefore that further equals half. Now BC is nothing but side A, and AD, as we have just proven, to be equal to B sine C. So therefore that proves the result for area of the triangle to be equal to half AB into sine C. Now we can prove the remaining two expressions by considering the remaining two sides as the basis, and so on. Now we have another formula for area of triangle, which is called as Heron's formula, and that is given by area of triangle ABC is equal to root of S into S minus A into S minus B into S minus C. where S is once again the semi-perimeter, so that is the already known symbol. Now in order to prove this formula, we take help of the previously proven formula of area. So let us start by writing area of triangle ABC as half AB into sin C. Now here what do we do is we write the sin C into half angle result. So sin C can be written as 2 sin C by 2 to cos C by 2. So here 2 gets cancelled and we have AB into, now in place of sin C by 2 and cos C by 2, we write their half angle formulae. So sin C by 2 is given by S minus A into S minus B upon AB inside the root multiplied by cos of C by 2, that is S into S minus C whole upon AB. So if you see, root A and root A gives us A and that gets cancelled with A. Similarly, root B and root B gives us B and that gets cancelled with B. So therefore, we have square root of S minus A into S minus B into square root of S into S minus C. So therefore, rearranging the terms inside the square root, we finally get S into S minus A into S minus B into S minus C inside the square root, which is nothing but the Heron's formula. Now we will solve few examples based on these results.